So I'm going to start with a bit revision of what we covered with David in the morning session. So he presenting something that was called the AI search ladder. The AI search ladder is pretty simple. We started out with the lexical search, classic BM25. We, discovered that with the rise of LLMs, doing the vector search and retrieving things into the model context is more helpful, but it's still not perfect. Then we discovered that, a combination of those two often performs better than the two versions just by themselves. And then we started thinking, okay, how do we automate things? The fourth thing that he presented was the end-to-end neural search that we are working on. But what is it really? I think if we look into this more closely, what we're trying to answer is, how can I search more efficiently across one modality? So this is when we tried to combine the vector search with the lexical search. Then the next stage is, once I achieve that, how can I search more efficiently across multiple modalities and across multiple clouds? Because typically this data lives in different clouds as well. And then the next stage, once that's kind of addressed, is how can I search with reasoning? How can I not only answer a simple question, but give the agent a very complex analytical question that you typically employ a person to kind of research and answer? And kind of finally is, how do I make this a self-improving cycle where we get the correct answer and then propagate it further? So the more searches are conducted, the better those agents get. And also, the more kind of data is generated in real life, that kind of informs the whole cycle again and again. So just briefly, how does this differ architecturally? First of all, with the lexical search, it's very straightforward. So everything is happening in memory. So you're searching through a bunch of data. Google did it perfectly. You retrieve, let's say, the top 10 results. You output it and you're done. And it's very kind of memory intensive process. With the RAG, with kind of hybrid search that we touched upon, we had the compute still contained the all these documents, and then you're doing a combination of different approaches, as I said, and the result is being fed into the LLM. For the next one, we tried to go into different modalities, and that required a little bit of tweaking of the architectural blueprint. So what happened was we thought, okay, we store separately the semantic data or the text data, and then we separately have let's say the images, in this case radiology images, and then we separately conduct the process in memory to try and retrieve what's the most relevant thing, and afterwards combine them and feed them into the context of the model. With the agentic RAG, it's slightly different because his agent in itself, like in terms of the inference, in terms of the reasoning, is pretty computationally intensive in itself. So I think what we started doing is we started thinking, okay, how do we kind of store it better, how we separate the processes? And that's where we started arriving at the fifth architectural problem, is when we said, okay, we gotta cut down some costs because this entire process is extremely expensive. So let's upload some of the data to the object storage. Store the scientific papers, because you're conducting a search and it's typically the same search, or a lot of you don't get a lot of different queries. You search for the same query but try different variations of it. So you upload the data to the object storage where it's much cheaper to kind of store and access it. Again, with the image data as well. And then for the compute part, you just keep the index. But for that, to keep the index in memory all the time is still pretty computationally intensive. This is, by the way, what the typical data warehouse blueprint would look like. So, compared to the previous approach, the architectural blueprint, you still get up to 5x improvement, but it's still super costly if you look and factor in the costs over the long run. So this is kind of what we start coming in. Why don't we offload the index to the object storage as well? So this is the exciting bit with Deep Lake V4, because what we're getting is the index and the data live on the object storage, so we free up a lot of resources that we can spend elsewhere. And now you may ask, okay, where is elsewhere? So this is kind of what we are doing. Oh, can you keep it on the last one? Sorry. So on the last part is what we're doing is we're trying to employ models like Colpally that we fine-tune and optimize for the multimodal retrieval, so that the ingestion part of the process yields us the most information that we can get from the data set, and the most context that we can then use to make the retrieval much more relevant when we retrieve it. So kind of to wrap it up, before we go to the more interesting part where Sasun shows the magic, there's like 3 things that I want you to remember. It's, first of all, this architectural blueprint that I just shown with Deep Lake V4, it's 10x more efficient, it's highly accurate, and it's truly multi-modal. So, I'll kind of repeat myself: 10x more efficient, highly accurate, and truly multi-modal. So just remember those 3 things, and this is right on cue for Sasun to demonstrate how this actually works. So please welcome Sasun, and thanks a lot for your attention.
Thanks, Mikayel. Yeah, my name is Sasun, and I'm going to show what it looks like to search truly on top of object storage. Yeah. So I prepared this Jupyter notebook where we'll be focused on just search part. We're skipping ingestion part for the demo purposes, but feel free to reach us if you're interested in other ingestion workflows too. Yeah. So let's get started. It starts with importing Deep Lake and loading Wikipedia. So this is the whole Wikipedia indexed and stored in Deep Lake with embeddings, and it contains 250 million rows and more than 3 terabytes data, and the index itself is 30 GB. Yeah, we can observe in summary of the dataset. It's binary quantized index embedding, and actually text and title of the Wikipedia is also indexed for the filtering search. Yeah. So next we're just having this example image for which we are generating description and trying to search Wikipedia for that description. So this is the image and this is the description which we get from OpenAI. And now we'll generate embedding for that and run this query, which is working on Wikipedia 250 million rows without using any cache. Yeah. Yeah. So the first run takes 2 seconds. It's because of some things needs to be fetched upfront, and actually we can observe the data which we get from the storage. Yeah. And then we can go ahead and try to apply some filtering here. This is our tensor query language. If you're not familiar with that, it's kind of extension of SQL with adaptation for multidimensional and index search purposes. So here we'll do text contains science, for example. Yeah. And if you look at the results, it's like different, and we actually can also print the scores. Just let me add some.
Drumroll.
Yeah. And initially it was like the scores were very high, but like because of applying filter, let's go back and run this again. You can see that initial scores were very high, like they were more similar. Yeah. But let's go further. Like this science, including like texts, are not satisfying. So we are like interested in scientific papers. Yeah. And we have another dataset, which is PubMed. It's like medical articles dataset with 41 million rows. And actually, this is not quantized. That's why index is like bigger. And we're on the same, like here, the embedding is different. So we generate it again with different model and run the embedding search here. And actually on this dataset, we have authors so we can observe them. And this is all happening on top of like object storage. You can see here that like we are not using any cache and memories. So this machine is 128 GB RAM, but we are using like, we don't need that much basically. And further going, like we have another dataset, which is like all the papers, not only medical, but also like other domain papers, and run the same query there. And this is again not quantized, so that index is like much bigger than this, this guy. And the same query here will give us like more broad results. And so these were like our text searches. And so we want to also show like directly searching image embedding on top of Lion dataset. So we have another one. We are loading Lion, which is like much bigger. This is 400 Lion. There is a version of Lion which is like 5 billion. This is next step for us, like to achieve. And it's ongoing actually. Thanks to
it's like 5 billion, but if you filter it for NSFW pictures, it's like much smaller.
Yeah. And the Nepal is used has like two embeddings actually, image and text. And we'll run 2 queries. So you can see that the dataset also has image embedding and text embedding. So first we'll run image embedding, again, cosine similarity. And we can get like the URLs of the images. The dataset itself does not have images stored. It's just keeping the URLs. And the scores are pretty high. And the text embedding, the last thing which we'll do, again, like the scores are high, and you did your similarity search, you can apply filters. I just skipped that now. And you can get like image URLs and just download them. Some random photos. So I was mainly focused on the like search part on top of object storage, and I run like couple of queries, but obviously this can be enhanced further, so that like the queries themselves can be run by agents, so that eventually you build this agentic search on top of object storage. Yeah, that's it. Thank you.
To kind of summarize basically what you saw, I think it's pretty awesome, is we show you the multimodality aspect of the search. So for your context, if you don't know, Leon is used to train models such as Stable Diffusion. We showed you the scale and the speed of a sub-second search with like very low memory utilization because we actually managed to, thanks to Sasun and our talented team, offload all the redundancies to the object storage. And we showed you the ingestion process. Well, not really showed you the ingestion process. It happened in the background, but believe us, it works. Powered by models like Copoly that are making extraction of multimodal data and structuring it much more easier. So thanks a lot for your attention. This is, by the way, not a demo that we'll show you, and it's available in 10 years. This is available right now, so you can pip install Deep Lake and try it right now. Awesome. Thanks a lot.